Video contains the solutions for your Chapter 2 multiple choice practice problems. And take a look at number 1. Looks like we have a piecewise defined function. Our f of x is equal to this when x is not equal to 2, and then otherwise it's equal to k. And if we want f to be continuous at x equals 2, then k must be, I think that's in another way of asking, what's the limit of this expression as x approaches 2? And whatever that limit is, that's where we need to plug that hole. I suppose we could check. The only way that this would actually be a legitimate problem is if plugging 2 in here gives 0 over 0, and quick check confirms that that's true, right? Otherwise it wouldn't be a pluggable hole or a fixable, a removable discontinuity. But it is, so we're going to multiply by the conjugate here. So let's see. If I multiply, I'm trying to find the limit as x approaches 2. Multiply this by the conjugate, that gives me the difference of 2 squares. So that's going to turn into that. On the bottom, I'll have x minus 2 times the whole big messy conjugate thing. I'm certainly not going to make any attempt to simplify that because I'm hoping, since 2 was the thing that was causing the 0, I'm hoping that this actually will cancel out, right? And on the top, 2x minus x is x. 5 minus 7 minus 2. The fact that we know that x minus 2 is going to cancel helps guard against making any kind of sign mistake, forgetting to distribute the negative sign, because this can't, if this was a 0 over 0 when you plug the 2 in here, it can't somehow turn into not 0 over 0 here until we cancel this out. So I think finally now we can cancel those out, leaving a 1 on the top. And now I plug in the 2, and I get that's the square root of 9 plus the square root of 9. That's 1 over 3 plus 3, or 1/6. All right, number 2. If f of x is equal to e to the x, which of the following lines is an asymptote to the graph? That's really a question about limits. It's also a question about pre-calculus knowledge of functions you should be familiar with. What does that graph look like? It looks like this, and it is in fact asymptotic to the x-axis, which is the line y equals 0. Right? This graph does not have any vertical asymptotes. I guess that was the only vertical asymptote choice. And it does not have a slant asymptote either. It doesn't approach any line like that. It bends way, way up much faster than a line like that, and that of course just cuts across it. That doesn't make any sense. And y equals 1, well, at least that was a horizontal line, but not the asymptote of this graph. Here's a super easy question. As n approaches infinity, same power, top and bottom, so that's the ratio of the coefficients of those highest powers, 4 over 1, which is 4. Which of the following functions are continuous for all real numbers? Let's see. Which of these functions have issues? Does this function have an issue? Well, that means it might be helpful just to think about that. What does it mean to raise something to the 2/3 power? It means to square it and then take the cube root. Are we going to have any issues doing this? And the answer is no, because you can take the cube root of anything, and also here we're making this positive anyway. Whatever x we plug in, x squared would be positive. So I think that this is continuous everywhere. There are no issues. There are no holes, vertical asymptotes, or anything like that. Y equals e to the x, we just sketched that function. That's continuous everywhere. But the tangent function, we know that that has that's got vertical asymptotes galore, as it does little passes like this from negative infinity to positive infinity. So that's not continuous everywhere. In fact, it has vertical asymptotes at all odd multiples of pi over 2, right? That's where they are. So it looks like 1 and 2. Those are the continuous ones. Number 5. If f is a continuous function defined for all real numbers x, and if the maximum value of f of x is 5 and the minimum value of f of x is negative 7, then which of the following must be true? And it looks like they're talking about some stuff with absolute values. Well, let me just sketch this. So wherever the function goes from, we don't really know about its domain, but we know that its maximum value is 5, so somewhere it gets up to 5, and then somewhere it gets down to negative 7, and it's continuous, right? So something like that. Then the maximum value of f of the absolute value of x, well, what would that look like? What does that do to a function? All the values that you were plugging in, you're now plugging in the positive version of those numbers. Right? So that's messing with x's, not messing with y's. Right? So, in other words, like if this happened over here, we would now be plugging in, instead of f of negative 2, would now be plugging in f of 2. So that means all the positive numbers that you were plugging in now are going to be the same as when you plug in the negative versions of those numbers. In other words, f of 2 would now be equal to f of negative 2. Right? Because of the absolute value signs, those would both become just f of 2. So that basically takes a function. Let me just use the space down here at the bottom and make a sketch for you. So for example, since we've been talking about the e to the x function, which looks like this, what would be the effect of, if this is f of x, what would f of the absolute value of x look like? Well, it basically obliterates this part of the graph and recopies this part for all of the negative numbers, because now f of negative 2 is the same as f of 2. F of negative 3 is the same as f of 3. So it would take that graph and make it look like this. So can we say that that is necessarily true? I think we cannot say that that is necessarily true, because what if that maximum value happened on this part of the function? What if it's had its maximum over here and then its minimum over here? It might lose that maximum value if it was in the part of the function that got obliterated here, right? If it was in the negative number domain part of the function. So I think we cannot say that that's true. Is the maximum, how about this? The maximum value of the absolute value of the function is 7. Well, what's the effect of putting absolute value signs around the whole function? The effect of that is it makes all of the y values, or in other words, the f of x values, positive. So it takes anything that's below the x-axis and then flips it up above. So I think that minimum that we used to have at negative 7 now in fact will be flipped up to here, and we will have a maximum of 7. So I think that this is true. And then the minimum value of f of the absolute value of x is 0. I think that that's not true either by our discussion here. If the minimum value happened over here when we flipped it, or when we flipped all those negative x values to positive x values, that just repeats the function here. So certainly it could still be below, right? You can still have f values of the function that are negative. Here we're just making the x values positive. So again, it recopies, it obliterates this side and obliterates this side and copies it here like this. So if you had a function that looked like that, say if that was f of x, then f of the absolute value of x is going to obliterate this side, leave this side perfectly intact, and then on the other side it's just going to recopy that. So certainly you can see these could be negative. So that doesn't mean that the minimum would have to be at 0. So I think 2 only is true. That's a pretty thinky problem there. Good one. Number 6. Another one of these easy ones. As n approaches infinity, highest power, top and bottom, 3 over 1. So that's 3. Number 7. If this graph has a horizontal asymptote, y equals 2, and a vertical asymptote, x equals -3, then a plus c must equal. All right, let's think about what that must mean. If there is a vertical asymptote at x equals 3, that's because we must be dividing by 0 when we plug in -3. So that means on the bottom, that must be x plus 3, right? That's how we end up with vertical asymptotes. So it looks like c is equal to 3. And now, if there's a horizontal asymptote at y equals 2, that's like saying the limit as x approaches infinity of this thing, of ax plus b over x plus 3, that means that limit must be 2, right? That's what it means to have a horizontal asymptote. And here's my highest power, top and bottom. So that would have to be 2x plus b over x plus 3, right? The ratio of those coefficients would have to be 2 over 1. So it looks like a would have to be equal to 2. So a plus c is 5. Number 8. The graph of the function f is shown in the figure above, right here. Which of the following statements about f is true? All right, so we're expecting 4 of these statements to be false then. So, is the limit as x approaches a equal to the limit as x approaches b? Well, the limit as x approaches a is 2, and the limit as x approaches b actually does not exist, right? Because it's 2 different things on the 2 sides. So that's no good. Is the limit as x approaches a of f of x2? Actually, we just said that, didn't we? So that looks good, but I'm just going to go through and check the rest to make sure that they're all false. The limit as x approaches b is not 2. It doesn't exist. So that's no good. Is the limit as x approaches b 1? No, it's 2 different things on 2 different sides, so it's not either one of those. It's like it's trying to be both at the same time. And what about the limit as x approaches a? Does not exist? No, it does exist. It's 2, right? So that is the correct answer. Number 9, we've got the limit as x approaches 1, x over the natural log of x. Well, let's see. Plugging in the 1, that gives me 1 over the natural log of x is, the natural log of 1, that's like saying, what do you have to raise e to get 1? You have to raise e to the 0 power. The natural log of 1 is 0. And if you look here, you might think, oh, that means we have to check the 2 sides. But notice that positive and negative infinity are not options here. And that leaves only non-existent as an option. And you find that if you do plug in numbers bigger and smaller than 1, you will get positive and negative numbers. It is going to be different on the 2 sides. We knew that this was not, it's not an indeterminate form because this is 1 over 0, not 0 over 0. So again, you always have to check before you try to do something else. Plug that number in. And here we've got if f of x is equal to the natural log of x from 0 to 2 and x squared times the natural log of 2 from 2 to 4, then the limit as x approaches 2. Well, let's see. As we approach on this side, here it would be getting closer and closer to natural log 2. And on this side, it would be getting closer and closer when I plug 2 in here to 4 times the natural log of 2. Those 2 things are not equal to each other, so that limit does not exist. It's coming into 2 different things. It's this on one side, and is this equivalent to any of the other answers? Would you pause for 1 second and just consider that? using your logarithm rules, this can come in as an exponent. 4 times the natural log of 2 is equal to the natural log of 2 to the 4th, or the natural log of 16. So that is actually the other side, but it's two different things on two different sides, and that means it's non-existent. Number 11. Function f is continuous on this closed interval from 0 to 2 and has values that are given in the table above. The equation f of x equals 1/2, that's a horizontal line, must have at least two solutions in that interval if k equals. And remember, solutions can be interpreted as intersections of the graphs, right? So I'm going to make a little sketch of this. Got the point 0, 1, and the point 2, 2. And we're interested in solutions to this function equals 1/2. In other words, intersections with this line. Well, if the function's continuous, it looks like if I pick any number below 1/2, then it would have to cross twice, right? It would have to cross once getting down to 1/2, or getting below 1/2, and then another time getting back up to here. So I think anything less than 1/2 would work. Would 1/2 work? I think no, because if you just put the point on that line, it could just like graze that and come back up, which would mean only one solution would be forced. But if it's anything less than 1/2, that's going to force it down, right? That would force it to cross here and then cross again. How do we know that it has to do that? Because it's continuous, because of the intermediate value theorem. Number 12. Graph of a function f is shown above. Which of the following statements about f is false? Is f continuous here? No. Well, I guess that's our answer, right? This is false. Right, you can't draw that without lifting up your pen to make that dot that seems to be in the wrong place. It's got a hole there, right? One of those points in the wrong place. Let's look at the rest of them and make sure that they are true. Does f have a relative maximum at x equals a? Well, we haven't talked in detail about exactly what that means, but it means exactly what you think it does. Like, in this neighborhood, is that the highest value of the function? And yes, it is. That's true. Is a in the domain of f? Sure it is. You can plug in a and you get that, right? So that's true. Are the two sides of the limit the same? Yes, they are. They're both coming into the same thing. That's true. And does that limit exist? Well, if they're the same, then of course the limit exists. So that's also true. So the one thing that's not true is it's not continuous there. And last one. If a is not equal to 0, then the limit as x approaches a of this expression is, well, let's see, that looks like it wants to be factored. So that would be the limit as x approaches a of x plus a times x minus a. And notice that when you plug in the a, you do get 0 over 0, right? So I'm hoping that since the a is causing the problem, I'm hoping that the x minus a factor will cancel out. Now, this is the difference of two squares, right? That's the same as x squared plus a squared times x squared minus a squared, right? And then this further factors into, I'm going to cross that out and replace it with x plus a times x minus a. So that's completely factored now. The x minus a factor, sure enough, it shows up on the top and the bottom. And there's also an x plus a that would cancel out, making our job a little bit easier. So now when I plug a in, I get 1 over a squared plus a squared, which is 2a squared.